Hello, this is Dr. Daystorms, and this is the third part of the thermochemistry chapter. And now we're going to be discussing enthalpy and what enthalpy is, and then discussing endothermic versus exothermic reactions and how we can determine that, and also like what a state function is, and review what an extensive property is. So, in the last segment, we were talking about the exchange of heat between system and surroundings. Because remember, energy is neither created nor destroyed, so it can only be transferred from one object to another in the form of either heat and or work. Well, when heat is being absorbed by the system from the surroundings, so heat is being added to it, it's called an endothermic reaction. And there's this symbol here called H, and we're going to talk about how that relates to enthalpy in a moment. So the delta H would be positive. It means it's endothermic. But there are also times whenever heat is released. And whenever the heat is released from the system to the surroundings, the delta H now would be negative. So the sign on delta H is a negative sign, and it's called exothermic reaction. This brings us to the idea of state functions. Because if we imagine, let's say that you walk in a lab and you find out that there's 50 grams worth of liquid water and it's at room temperature, it's 25 degrees Celsius. That's what it is. That the internal energy, you can figure it up right there, but you don't know how it got there. And so many times we have no way of knowing the actual internal energy of a system because it's too complex, and we also don't know how it got there. And so, for example, did this system actually start out as 50 grams of water at 0 degrees, and then it was heated up and it melted to become 50 grams of water as a liquid at 25? Or did it start off at boiling, or almost boiling, 50 grams of water around 100 degrees Celsius, and it cooled down to 50 grams of water at 25 degrees Celsius? I mean, we don't know the path that it took. We just know what the state of that is at that time. Okay? So the water could have reached the room temperature from either direction. Therefore, the internal energy is called a state function. We don't know how it got to that energy state, but we just know that whatever pathway it took, it ultimately got there. And so that's why it's called a state function. State functions depend only on the present state and not on that path. So delta U depends only on U final and U initial. And that's where we got this idea that we could say delta U was equal to U final minus U initial. It doesn't say how it got there, like what pathway it took, but that's just what delta U is. So if we look at this example here, we start off with a charged battery. The charged battery has a certain amount of internal energy, and then you find it later on. Say, for example, you're married and your wife has put the battery back in the drawer and it's dead. Not speaking from experience here. It's a discharged battery now. We don't know how the charged battery became discharged. Did it become discharged because it short-circuited, so it lost it all due to heat? Or did it become discharged because it lost some of it due to heat, and then the rest of it because it had been running the fan for a long period of time? Okay, so we don't know how it got there, but we know it's there. So that's why delta U, or delta E in the way this is showing, is a state function. But you notice, let me erase some of this. Delta U is a state function. However, heat, which was Q, technically it's supposed to be a lowercase q, and work, which is W, are not state functions. Those matter. Was Q a large Q here, and a small one there, Or was it all work, or was it a certain amount of work? So Q and W are not state functions, but delta U or delta E is. So you just have to be careful here. Remember, a state function means you don't know how it got there, but you just know what phase it's in, and then, but it can be composed of different variables that are not state functions, like Q and W do matter by the path. There are different types of systems. You can think of one that's an open system. And so the open system means, for example, you just have water boiling in a beaker and just the vapor is just escaping into the big room at large or boiling outside, and you have the door or the window open and it's just going away. So it's an open system. You can also have a closed system, and you can have an isolated system. So many times here we're talking about a closed system where it can't escape. Okay? So let's, for example, show here, this is an open container, but we have a piston to where we can actually measure the change in the volume. Okay, so we have the initial state, you've got some type of gas in the piston. As you heat it up, then the gas actually will start to expand and does work, and it moves that piston because it's not completely isolated, completely closed, and you're actually able to measure the change in the volume. Okay? And so the only work that's being done is the way that the gas is pushing on the surroundings of the piston and moving it up. So we can actually measure the work done by gas if we're using something like a piston system. And here's just another example. This is actually a reaction that you may have done already in lab, where you've taken hydrochloric acid and we drop some zinc in it. Of course, there's reaction. This is a metathesis or an exchange reaction, and one of the products that's given off is going to be hydrogen gas. So the hydrogen gas starts to escape, and whenever it escapes, it pushes on this piston to move it up. So that's why you can actually measure the volume that the piston has moved, and that volume is due to the gas. Since the pressure of the entire system is not changing, we can actually consider it's a constant, and so the work is going to be equal to negative, because the system is doing the work on the surroundings, on the piston, times the pressure, times the change in volume. So, the way that this relates is that anytime you have this process, and there's a constant pressure, which almost everything that we do in chemistry and in biochemistry, it's at a constant pressure. The only work done can be accounted for by the fact that it's due to the heat flow. And so this is called enthalpy. So enthalpy in a constant pressure environment is equal to heat. So that's why many times we actually use them interchangeably. So let's say the enthalpy of a reaction is the heat of a reaction, which that's only true under constant pressure. However, it's a moot point for most of the time in chemistry and biochemistry, since we are, our bodies are at a constant pressure for the most part. Okay, so enthalpy is the internal energy plus the product of pressure and volume. So, if we want to do the math, and we're trying to use this algebraically rather than calculus, you have delta H is equal to delta, which is a change in that U plus PV. However, since sum of the constant, you can actually then pull the P out. So we just cross-multiply, not cross-multiply, but we multiply, so it's going to be delta U plus delta PV. However, P is not changing, so P is a constant. So it comes out of the delta. So now the change in the enthalpy is equal to the change of the internal energy plus P delta V. since U is equal to Q plus W, and W is equal to minus P delta V, we can actually substitute these. So what does that mean? Now we have delta H is equal to Q plus W plus a negative, P delta V. But we just said that under these conditions that W, I put the wrong sign in, I'm sorry, plus P delta V. But since we said that W is equal to negative P delta V, we're going to have delta H is equal to Q plus a negative P delta V plus a P delta V. And so that means that delta H truly is equal to heat in this instance. So whenever pressure is constant, the change in enthalpy is the heat gained or lost. I can't stress that enough. So since most of the conditions that we're working under, the overall pressure is constant, then we can simplify enthalpy down to heat. Why is this important? This will let us know for sure that now we have any time that the delta H is positive, it's going to be an endothermic reaction. And any time that the delta H is negative, it's exothermic. So let's take it one step farther. So now delta H is much like delta U. In the event that we can see the change in the enthalpy, or the change in the heat, is going to be equal to the heat of the products minus the heat of the reactants. And I won't give you this equation. So you just need to remember that delta H is equal to H of the products, or the final state, minus H of the reactants, or the initial. So it's always products minus the reactants. And this is just showing you that whenever we say that we're going from, this is the combustion reaction of methane to form carbon dioxide and water, and we can see that 890 kilojoules of heat, kilojoules of energy, is given off. So it's an exothermic reaction. In theory, if you could cause it to go backwards, 890 kilojoules of heat would have to be put into the system. But of course we can't. That doesn't work under normal conditions. And so this delta H quantity is often called the enthalpy of reaction, or the heat of the reaction. And this is something, this is showing the combustion of hydrogen gas and how it's very exothermic. A lot of heat is given off. But this is something that you can actually look up in many tables. So let's discuss the truth about enthalpy. Enthalpy is an extensive property. So do you remember what that means from earlier this semester? It means it depends on how much you have, which should make sense. If you just have a little bit of methane gas, you're only going to give off a little bit of heat. If you have a lot of methane gas, it's going to be a huge explosion and give off a lot of heat. The delta H for reaction in the forward direction is equal in size, but opposite in sign to the delta H for the reverse. So negative 890 kilojoules of heat are given off, but it would take positive 890 kilojoules of heat to go into the system for it to go backwards. You just have to change the sign. And that delta H for the reaction does depend upon the state of the products and the state of the reactants. A liquid would behave differently than a gas or a solid. So let's do an example. This is a little tricky here. Hydrogen peroxide can decompose to form water and oxygen by the following reaction. And so they've already balanced it for you. First of all, you would want to make sure it's balanced, but this one's already balanced. So we have 2 moles of hydrogen peroxide liquid goes to form 2 moles of water plus 1 mole of oxygen gas, and they tell you that the delta H for this reaction is negative 196 kilojoules. So first of all, is this an exothermic or an endothermic reaction? Since delta H is negative, whoops, that came out a little darker than what I meant. Since delta H is negative, it's going to be an exothermic reaction because it's giving that heat off. So what does that really mean? This means that 196 kilojoules of heat is given off for every 2 moles of peroxide liquid. It also means that when you make 2 moles of water, negative 196 kilojoules of heat's given off. Okay? So it's stoichiometrically related. Okay? Well, we're not given moles in our problem. We are given grams. So remember, we're going to have to figure out the molecular weight of hydrogen peroxide in order to convert from grams to moles. So let's do that. So let's figure out the molecular weight of H2O2. We look on the periodic table. We have 2 oxygens, and they are 16. Plus, we have 2 hydrogens, which is 1.01 each. Would give us a molecular weight of, let's see, 3402 grams per mole. And I'm going to change colors so that way it's a little easier to tell. Okay, so we start off with 5.00 grams of H2O2. We know that 34.02 grams of H2O2 is equal to 1 mole of H2O2. But from the reaction up here, we can see that 2 moles of H2O2 gives off negative 196 kilojoules. So we have 2 moles of H2O2 gives off negative 196 kilojoules of heat. So let's figure out the value of the heat, or how much heat is not given off. Let's make sure that everything cancels that should cancel. We have grams of hydrogen peroxide, grams of hydrogen peroxide, moles of hydrogen peroxide on the top, moles of hydrogen peroxide on the bottom. So the only thing left is kilojoules, which that's what we're looking for. So now we get to just plug and chug. You multiply by everything on the top, so we have 5.00 times negative 196. You divide by everything on the bottom, so we divide by 34.02, and you divide by 2. You get the answer, negative 14.4 kilojoules. I just ran out of room, so that's why I put it underneath. So that's how much heat would be given off whenever hydrogen peroxide decomposes to, whenever 5 grams of hydrogen peroxide decomposes to form water and oxygen gas. So I hope this has helped explain what enthalpy is, and to work with that we were able to work through an example of using enthalpy to figure out how much heat would be given off in a reaction of a certain amount of a product. I will see you in class. Until next time, take care.